Part 4 of Unit 13 is about KSP, solubility product to equilibrium. Okay, let's learn about solubility products. Let's consider the equilibrium that exists in a saturated solution of barium sulfate in water. Well, barium sulfate is insoluble. It's a solid. You know those solubility rules you spent so much time learning, and you learned that list of things that made solutions insoluble and form precipitates? Well, we're going to ruin that now, because everything is soluble to a certain degree. So if barium sulfate was going to dissolve, it would dissolve in equilibrium with a barium ion and a sulfate ion. Barium sulfate just happens to have a very, very low solubility, so we were considering it insoluble for net ionic reactions. If we were to write an equilibrium expression for this equation, well, we know that solids don't show up in an equilibrium expression, so KSP expressions are easy. The equilibrium constant of the solubility product, that's what the SP stands for, is just going to be the barium ion concentration times the sulfate ion concentration. So these equilibrium expressions are actually relatively easy to deal with. Now, one thing we need to know about solubility products, KSP is not the same thing as solubility. Solubility is the mass of something that can be dissolved in a given volume of liquid, usually given in grams per liter or grams per milliliter. That can be converted to KSP by using the formula weight or molar mass of the substance to end up with the molarity of that substance, and then using the molarity in the formula to find the molar concentration of all the different ions. Then we can determine KSP from that. But we need to know that KSP, the solubility product constant, is not the same thing as solubility. There are some factors that affect solubility and KSP. We just need to remember that they're different values. Those factors are the common ion effect. If one of the ions in a solution at equilibrium is already dissolved, the equilibrium will shift to the left and the solubility of the salt will decrease. So if we were looking at this barium sulfate reaction right here, if we were trying to dissolve barium sulfate in sulfuric acid, H2SO4, that means there's already going to be lots of sulfate ions present. That's going to cause a shift, and Le Chatelier's principle says that since we have a stress of extra sulfate, it's going to shift to the left. That means there's going to be less barium sulfate that dissolves. pH can also affect solubility of a substance. If a substance has a basic anion, it'll be more soluble in an acidic solution. If a substance has an acidic cation, it's more soluble in a basic solution because it's more likely for neutralization reactions to happen. KSP values are useful in determining if a precipitate will form in a given situation. We can go back to using the reaction quotient for this. So if KSP is less than the reaction quotient, that means it's going to shift to the left and it's going to make more precipitate, because the solids are on the left side of our KSP dissociation reactions. If KSP is equal to Q, that means the solution is at equilibrium and it's said to be saturated. It can't hold any more dissolved product in it. If KSP is greater than Q, it's unsaturated, so that means more solid will dissolve. Let's look at some examples of KSP calculations. KSP of calcium fluoride is 3.45 times 10 to the negative 11th. We need to calculate the molar solubility of calcium fluoride at 25 degrees Celsius. Then determine the concentration of each ion at equilibrium. Well, our reaction is calcium fluoride, solid, at equilibrium with a calcium ion and 2 fluoride ions. If we fill out the rest of our rice table, we remember that solids don't do anything, and we didn't have any of this at the beginning, so we end up with plus x plus 2x because of the coefficient 2 in the balanced equation. So at equilibrium we have x and 2x. Now we can use the KSP value to solve for x, and in the KSP problem, x is called your molar solubility. So I'm going to clear this off of here. So KSP is equal to the calcium concentration times the fluoride concentration squared. We have to remember to square that from the 2 in the balanced equation. So KSP is 3.45 times 10 to the negative 11th. That's equal to x times 2x squared. So 3.45 times 10 to the negative 11th is actually equal to 4x cubed. We have to remember to square the coefficient as well as the variable. When we solve this, x ends up being equal to 2.05 times 10 to the 4th. Negative 4th, excuse me. So that's x. This is my molar solubility. Now the rest of the question was asking about the concentration of each ion at equilibrium. Well, calcium was just x, so the calcium concentration is 2.05 times 10 to the negative 4th. The fluoride concentration was 2x, so we have to multiply that by 2. It's 4.1 times 10 to the negative 4th. So the important thing to remember here is the 2, both in the 2x and the exponent of 2 in the KSP expression, and know that molar solubility, whenever you solve for that, is x in your rice table setup. Your question for this section: KSP of aluminum hydroxide is 2.0 times 10 to the negative 32nd at 25 degrees Celsius. Calculate the molar solubility of aluminum hydroxide.